Hi everyone, welcome to my channel. Myself Ram Reddy, studying in Sri Venkateshwara College of Engineering, Bangalore. Today we will discuss about binary counter with multi-threading and stack implementation. My team members are Ravitej, Ravindra and Raviraj. Introduction to binary counting with multi-threading and stack implementation. Binary counting is a fundamental concept in computer science and digital system as it forms the basis of all the modern computation. In binary counting, numbers are represented using only two digits 0 and 1. They are corresponding to the off and on states in digital circuits. The simplicity allows for efficient computation and storage in binary based systems. When combined with multi-threading, binary counting can be optimized for parallel execution, improving performance in multi-core systems. Multi-threading involves dividing a task into smaller threads that can execute simultaneously, allowing for faster processing. For example, in binary counting, multiple threads can independently handle different ranges of numbers, enabling concurrent computation. A stack is a data structure that operates on the principle of last in, first out. Stacks are widely used in binary counting and multi-threading for various purposes, such as storing intermediate results, maintaining execution context, and managing recursion. Implementing binary counting using stacks ensures an organized way to track the current state during computations. By integrating binary counting, multi-threading, and stack implementation, we can create efficient algorithms that take advantage of parallelism and structured data management. This approach has applications in areas such as simulation, cryptography, and real-time system where speed and reliability are crucial. Literature survey: Parallel digital decoding. Research in parallelism has led to improvement in the performance of decoders, especially in systems requiring real-time decoding. Memory management in decoding. Studies on memory management highlight strategies to optimize the handling of arrays, especially in memory-intensive tasks like decoding, threading, and synchronization. Various multi-threading models have been explored to speed up decoding operations. Error correction in multi-threading system. Decoding often involves error correction algorithms which benefit greatly from threading and array management. Real-time decoding systems. In real-time applications, ensuring that the decoder operates efficiently and without delay is critical. Applications: Task ID generation. Unique IDs using automatic binary counter updates. Stack stores unused IDs for recycling. Thread synchronization. Binary counter as a semaphore to manage access to shared resources. Stack tracks thread states of rollback. Resource management. Bitmask operations with binary counter and stack for resource allocation. Parallel depth limitation search. Stack stores nodes while the binary counter tracks depth. Load balancing. Stack queues tasks and binary counter tracks progress in multi-threaded environments. Benefits: increased performance. Multi-threading speeds up task execution by running tasks concurrently. Efficient resource management. The stack efficiently manages and recycles task states, minimizing memory usage. Scalability. The system can easily scale to handle more threads as the workload increases. Simplicity. Binary counters and stacks are simple to implement and integrate into existing systems. Reliability. Thread-safe operations ensure consistent and error-free execution
Now let's
across
see
threads.
the code of digital decoder with thread synchronization and array management. Hash include studio.h, hash include pthread.h, hash include stdlib.h. Define the maximum number of threads. Hash define maximum thread 5. Hash define array size 10. Mutex of thread synchronization. Pthread mutex t mutex array to store decoded values, initiated decoded values, array size. Digital decoder function decodes a 4-byte binary number into its decimal equivalent. Initiated digital decoder initiated binary input. If binary input 0, binary input 15. Printf invalid input, it should be between 0 and 15 into binary input return. binary input simple decoder binary to decimal, thread function for decoding and storing values, wide decode and store wide, initiated index get index from the argument passes, simulative byte binary input of example 0 to 15, initiated binary input, lock the mutex before accessing the share, maximum of the decode the binary input and store the shared array, print decoded result, print of thread and decoded values, unlock the mutex of updating of array, pre-thread and mutex unlock, return initiated main, initialize the mutex, pre-thread mutex initiated, print of the mutex initialization failed, array of thread, create thread to perform decoding for initiated maximum threads, initiated index, allocate if index, print of the memory allocation failed, index assigned thread index, if thread creates null, decode and store, the next thread creation failed, next waiting for all thread to finish, initiated pthread join threads, print the final decodes values, print of the decoded values in array, index in decoded values, clean up the mutex, pthread mutex destroy mutex, correct the return statement, thread 1 decoded value, 2 decoded value, 3 decoded value, 0 4 decoded value, decimal values in array, index 0 9.
Results and outcomes. Announced performance tasks are executed concurrently, optimizing CPU utilization. Scalability. The approach supports increasing workloads by adding more threads, efficient resources usage. The stack ensures minimal overhead by recycling states and managing task dependencies. Rubbishness. Proper synchronization ensures system reliability and prevents errors like race conditions or deadlocks. Advantages. Performance. Multithreading boosts execution speed by dividing tasks among threads. Efficient resources allocation. Binary counters provide lightweight tracking of states or IDs. Simplicity. Binary counters are easy to implement and integrate with multi-threaded systems. Stack simplify state management and backtracking. Thread safety. Thread safe implementations usage locks or atomic operations ensure data integrity. Flexibility. Reusable components. Binary counters and stacks can be adapted for diverse applications like task scheduling, memory management, or DFS. Resources optimization. Minimal memory overhead due to compact representation in binary counters. Stack efficiently recycles resources or states. Rubbishness. Stack store states enabling recovery from incomplete tasks. Ensures correctness even in failure scenario or during backtracking. Scalability. Well suited for handling increasing workloads by adding more threads. Disadvantages. Complexity synchronization. Race conditions requires carefully synchronization, adding complexity. Overuse of logs may lead to contamination, slowing performance, deadlocks, and stratification. Improper handling of locks can cause deadlocks. Threads may be strayed if take operations are not well managed. Overhead. Maintaining thread safe stacks and counters introduces processing overhead. Excessive use of multi-threading can result in context switching, degrading performance. Debugging challenges. Multi-threaded environments make it harder to trace issues like race conditions or deadlocks. Stack overflow errors are possible if recursion or state management is not optimized. Limited scope of binary counter. Binary counters are best suited for simple tracking tasks. For more complex requirements such as a priority based task management, additional logic is needed. Hardware thread performance depends on the underlying hardware's ability to handle parallel execution limited thread support on older systems can reduce
Conclusion. Parallel processing efficiency. Multithreading improves throughout the digital decoder by all concurrent decode of data, which reduces the overall process time. Thread synchronization. Mutex looks to ensure the data integrity when multiple threads are access shared resources, prevent the conflictuality, and ensure the safe update to the shared array. Efficient memory management. The proper array management minimize the size of fragmentation and ensure the optimal use of the system memory, reducing the overhead and preventing the memory leaks. Bibliography is a P-thread programming, a POPIX standard for the better multiplexing, and K. Robbins K. H. Robbins Polymedia in 2004. Threading in with P-thread J.R. White in 2005. Operating system and digital design and implementation. A.S. Thumbin H. was and third edition of Peterson Hall in 2006. Thank you.